A resistance thermometer measures temperature by measuring the change in resistance of platinum. A platinum resistance thermometer has a resistance of 225 ohms at 20.0 degrees Celsius. When the thermometer is placed in a furnace, its resistance rises to 448 ohms. What is the temperature of the furnace? Assume the temperature coefficient of resistivity is constant over the temperature range in this problem. The resistivity of platinum at 20.0 degrees Celsius is 10.6 times 10 to the minus 8 ohm meters, and its temperature coefficient of resistivity is 3.64 times 10 to the minus 3rd degrees Celsius. Now this is a practical example. So resistance thermometers are thermometers that measure resistance based off of temperature. This is because we know that resistivity for conductors varies with temperature, and to a decent approximation, the resistivity of a conductor is equal to the resistivity at some reference temperature, which is taken usually to be 20 degrees Celsius, times 1 plus the temperature coefficient of resistivity, which we call alpha, times, and here's the temperature dependency, times the temperature minus our reference temperature, again, usually at 20 degrees Celsius. Now, remember, for conductors, resistance is equal to resistivity times the length of the conductor over the cross-sectional area through which current moves. What this says is that there is a temperature dependence of resistance. And so resistance thermometers work because we take resistors that we know very well their behavior based off of temperature changes, and we measure the resistance. If we find that a resistor has a certain resistance, then we know that it's operating at a particular temperature. So in this problem, we have a platinum resistance thermometer, and we're going to use it to measure the temperature of a furnace. And we're going to do that by knowing what its resistance is at 20 degrees Celsius and what its resistance is when it's in the furnace. So to begin, let's do a couple of sketches. The first sketch is just going to represent our wire at 20 degrees Celsius. So at 20 degrees Celsius, our wire is going to have some length, and it's going to have some cross-sectional area, and it has a particular resistivity and a particular resistance. So the resistance at 20 degrees Celsius is given as 225 ohms. The temperature is, 20 degrees Celsius. And the resistivity at our reference temperature of 20 degrees Celsius is given as 10.6 times 10 to the minus 8 ohm meters. And we're also given the temperature coefficient of resistivity to be 3.64 times 10 to the minus 3 degrees Celsius. So we know what the resistance is of this thermometer at 20 degrees Celsius, or of this resistor at 20 degrees Celsius. Now we're going to place this resistor in a furnace. So once it's in a furnace, it's going to get hot. Let's assume that neither the length nor the cross-sectional area will change by a measurable amount. So we'll assume those two quantities remain constant. Being placed in this oven, the resistivity of our thermometer will change because resistivity is dependent on temperature. I'll just call that resistivity X, X being an unknown temperature. Now the resistance is given, and the temperature is unknown, but that's what we're trying to find. So let's write those quantities down. We don't know the resistivity. Well, actually, let's start off with what we do know. We know that the resistance in our furnace is 448 ohms. The temperature in our furnace is unknown, but that's what we're trying to find. And the resistivity of our thermometer, we don't know that yet either, but we do know its form, that it's equal to the resistivity at our reference temperature times 1 plus the coefficient of resistivity times the difference between our temperature of the furnace and our reference temperature. We're trying to find the temperature of the furnace. So to find the temperature of the furnace, since we know the resistance of our thermometer when it's in the furnace, let's use the relationship between resistance and resistivity. We don't know the length of our conductor, and we don't know its cross-sectional area, but that's okay because we know information about those two quantities based off of the fact that we know the resistance of our thermometer when it is at 20 degrees Celsius. So here we know the resistance, we know the resistivity at 20 degrees Celsius. Let's get our expression for L over A, because those are two unknowns we don't have, and let's express L over A in terms of our resistance and resistivity at 20 degrees Celsius. This means that our resistance in our furnace is equal to the resistivity of our thermometer times the resistance at 20 degrees Celsius over the resistivity at 20 degrees Celsius. So let's call this equation 2. Let's call this equation 1. And what we're going to do is we're going to plug in equation 1, our resistivity in our furnace. We're going to take that expression and plug it into equation 2. So plugging equation 1 into equation 2, we get the resistance in our furnace is equal to the resistivity, and this is the resistivity at our reference temperature, plus 1, or times 1, plus the temperature coefficient of resistivity, times the difference between our temperature in the furnace and our reference temperature. So this expression right here is our resistivity, and that is times the resistance at our reference temperature over our reference resistivity. Notice that the resistivity of our reference temperature cancels because it's in the numerator and the denominator. And this gives us our resistance in our furnace over our reference resistance is equal to 1 plus alpha times the temperature difference between our furnace and our reference temperature. Isolating the temperature difference, we end up with 1 over our temperature coefficient of resistivity times the ratio of the resistance in our furnace to our reference temperature minus 1. Isolating the temperature of our furnace, we get the temperature of our furnace is equal to our reference temperature plus 1 over the temperature coefficient of resistivity times the ratio of the resistance in our furnace to our reference resistance minus 1. Let's plug in values for this. So the temperature in our furnace is equal to our reference temperature, which is 20 degrees Celsius, plus 1 over the temperature coefficient of resistivity, which is 3.64 times 10 to the minus 3 degrees Celsius. Oh, and I'm noticing I have a mistake in the problem statement. This shouldn't be degrees Celsius. This should be per degree Celsius. Okay, so we have that per degree Celsius now. And this is times the ratio of the resistance of our thermometer in our furnace, which is 448 ohms, over our reference resistance, which is 225 ohms, minus 1. Canceling units, we see that each term on the right-hand side has a degree Celsius in the numerator because this per degree Celsius comes on top. When I plug this into my calculator, I get that the furnace's temperature is at 292 degrees Celsius.